In 1905, Albert Einstein published 5 revolutionary papers on physics. One of those papers, titled On the Electrodynamics of Moving Bodies, now known as Special Relativity, redefined what we mean by space and time. It showed that time as an element is not universally the same, but it moves differently for everyone depending on their motion. For an object moving very fast, time would pass more slowly compared to an object at rest. To understand how, we have to go back in time literally. Suppose we are standing 100 meters away from each other. I ask you the location of our vehicle, and you say it is 50 meters to the right. Is it your right or my right? This is an important question because the position of objects in space depends upon the frame of reference. You need to clarify whether you are referring to an object from your perspective or mine. This is an example of coordinate system. Now, if you see another vehicle move past in front of us, the direction of its motion will be different. If I see the vehicle moving to my right, you will see the vehicle moving to your left. Similarly, if a train is moving at a speed or velocity of 20 meters per second in a train station, a person standing outside the train on a footpath would observe the train to be moving at that 20 meters per second velocity. However, a person inside the train would observe no velocity of the train at all, given all windows are closed. That is because the person inside the train is moving with the same velocity of the train. All motion here is frame dependent. Now, if our trained person throws a ball at 10 meters per second, he will observe the velocity to be 10 meters per second. However, if the person outside on the footpath could observe this ball, he would observe the velocity of the ball to be traveling at 30 meters per second. Velocity of the ball plus the velocity of the train. This is because velocities add or subtract depending on the frame of reference. This is a part of classical mechanics described by Isaac Newton. One thing of note is that all motion talked here is only uniform motion. Motion of an object that is either moving at a constant velocity or is at rest. This is known as inertial motion. The same object can really be in a uniform motion or at rest. If I am standing still and observe a bird moving at a velocity of 10 meters per second, you will not observe the same velocity of the bird if you were on a bicycle that was also moving at 10 meters per second. In your frame of reference, the bird is not moving at all. We are both talking about an object that is in an inertial motion. Galileo described this in 17th century, stating that there is no privileged frame. All laws of physics work the same for everyone in every inertial frame. However, all motion is relative. This is known as the principle of relativity. Up until the 19th century, classical mechanics was working all along and made sense. However, things later stopped making sense, particularly when it involved the speed of light. If we revisit our train station example, and this time instead of giving a ball to our person, we give him a flashlight. When that person turns the flashlight on, he will observe the speed or velocity of light to be roughly 300,000 kilometers per second. This is the velocity of light in a vacuum. To simplify things, we will assume this speed to be equivalent to 1c. Now, as per the rules of velocity addition as we discussed earlier, the person standing outside on the footpath should observe this velocity of light to be 1c plus the velocity of the train, which we set as 20 meters per second. But he will not observe the speed of light to be point faster than 1c. The velocity of the train and the light are not adding, but as per the principle of relativity, the laws of physics of adding or subtracting should work like all other laws. And it does work as long as the velocity is not as fast as the velocity of light. You see, it turns out that the velocity of light remains constant in all inertial frames. Velocities stop adding beyond the speed of light. What this means is that we have found the universe's speed barrier, that nothing can travel faster than the speed of light. All the information and physical effects of the universe cannot travel faster than light. Information to any observer will not reach faster than speed of light. For example, it takes 8.3 minutes for light from the sun to travel to us on Earth. If the sun were to disappear suddenly, Earth would continue to orbit normally, and we wouldn't even notice any effects until after 8.3 minutes have passed. This speed limit also led to some interesting consequences discovered by Einstein on how we observe space and time. Like time would pass more slowly the faster you move. But before we move on to that, there is an important thing to discuss. Events that happen for one observer may not happen at the same time or place for another observer. Let's put 2 points at the start and end of our footpath. We will call them point A and point B. Suppose 2 lightning flashes strike at the same time simultaneously, one at point A and another at point B. To exactly know for certain that the lightning struck simultaneously on these points, we will put an observer with 2 mirrors at the middle point of lengths A and B. We will call this point M. Now, if our observer at point M sees the flashes at the same time in his mirror, we can say for certain that the flashes occurred simultaneously. Now let's put another observer inside a moving train's middle point. We call that point T. We set the train's length exactly the same as our footpath. And just when the train's T points lines up with the footpath's M point, flashes of lightning happen again simultaneously for the observer at the footpath, but for our observer inside the moving train, the flashes don't occur simultaneously. In fact, for him, the flash from point B arrived earlier than from point A. What happened here then? Did the velocity of light changed? No, but something had changed. The observation of the order of events. What seemed to occur simultaneously for our observer on the footpath did not occur simultaneously for our observer inside the moving train. Time here is compensating for the constant velocity of light. And it turns out that time is not absolute but relative. It is different for every observer depending on their or the object's velocity. 2 things happened for our observer inside the moving train. Firstly, because the train was moving towards point P, just when the flash of lightning occurred as per our observer on the footpath, the flash of lightning at point A had to travel more distance to reach the point T because of the velocity of the train that was moving towards point B, and the flash at point B had to travel lesser distance to reach point T. Secondly, time for the observer inside the moving train slowed down when compared to our observer on the footpath. Now this is a half-lie. Earlier, by saying that time is not absolute but relative, what was meant that just like the motion of an object in classical mechanics, time is also relative. Let's look at an example. We have one observer stationed at Earth and another who is moving inside a spaceship at 90% the speed of light. Time for our observer on Earth according to his wristwatch is moving normally. 1 second is equal to 1 second and his heart is beating at a normal rate. Similarly, time for our observer on the moving spaceship according to his wristwatch is also moving normally. But if the observer on Earth could see the time on the observer's wristwatch in the spaceship, the observer on Earth would see it moving about 56% slower. This means that from Earth's perspective, every second that passes on the spaceship, more than 2 seconds would have passed on Earth. This is known as time dilation. The real effects of time dilation is observed inside particle accelerators, where an unstable particle speeding inside the accelerator is observed to have a longer half-life than its counterpart at rest, because for us, time of the moving particle is ticking more slowly. Do note that in special relativity, time is passing normally for every observer according to their watches, but it only differs when they compare their own time with each other. Time here is not constant but relative. Just like there is no privileged frame for motion, there is no privileged frame for time. All motion is relative, all time is relative, and it turns out all distance or length is also relative. Distances measured by 2 observers will also be relative. To describe this phenomena of length contraction, we move back to our example of the footpath and the moving train. If you remember, we called the starting point of our footpath point A and called the end point B. Now our observer on the footpath measured its size to be 100 meters. And when we built our train, we made sure it was also 100 meters long. We were certain of its length because it measured exactly the same as our footpath from point A to B. We also set the train moving very fast. Importantly though, our observer inside also had a measuring stick that measured exactly 1 meter. Inside the moving train, our observer was tasked to measure the train. Using his measuring stick, he measured it to be exactly 100 times the measuring stick, which comes at about 100 meters in total. All looks good so far, except when the moving train passes by our footpath, our observer on the footpath does not measure the train to be exactly 100 meters at that instance. He measures it a little shorter. What just happened here? Didn't we just measure the train to be exactly 100 meters? Our observer inside the train also measured it to be 100 meters. It turns out that just like time, length also changes for moving objects and observers. From the footpath's observer, the train's velocity caused the length of the train to contract or shorten alongside everything that was inside the train, including the measuring stick. The velocity contracted the train just enough to make a length difference when it passed along our footpath. Similarly, for the moving train observer, the footpath would appear contracted. Einstein discovered that alongside motion, time and length are also relative. What remains constant everywhere for every inertial observer is the speed of light in a vacuum. This together makes up the continuum of four-dimensional space-time. Hermann Minkowski in 1907 published a paper on spacetime that was consistent with Einstein's theory of special relativity. It essentially treated time as an extra dimension in a continuum known as spacetime. You can think of 4D spacetime as a plane where instead of just 3 dimensions of space, there exists a 4th dimension of time as well. This profoundly expanded our understanding of physical reality. Similarly, the Lorentz transformation equations are the math that is used to calculate different motions in special relativity. Einstein called his theory special theory of relativity because it was restricted to a frame's uniform motion. You see, special relativity works as long as all motion is inertial and doesn't involve any significant acceleration or gravity. In fact, it can work well when little acceleration or gravity is involved, but when they become extreme, things become complicated. 10 years later, Einstein devised another framework that worked with extreme velocities and gravity. The work is known as general relativity, a topic perhaps for next video. We don't necessarily need the theories of relativity to describe all motion. In fact, the old motion laws of Newton still work alright as long as the velocities involved are not very fast. As a consequence, or rather using the same basis that led Einstein to develop special relativity, he went on to predict that mass and energy are equivalent, expressed by the formula E equals mc squared, one of his most famous works. To sum up special relativity altogether, as objects accelerate towards the speed of light, they become shorter in the direction they are traveling, their energy becomes greater, and time passes more slowly for them. One object that does travel at the speed of light is the particle of light itself, the photon. If the photons could observe the universe, to them everything would look like a singularity, where perhaps time and space are all but one tiny dot.